Good morning, students. This week we talked about forces. So, what is a force? A force is a push or a pull that an object feels when it interacts with another object. For example, here we can see that this guy is pushing the cart, and over here we can see that the lady is pulling the flower. This interaction can be with physical contact, like in these two cases, or it can be indirect or non-contact. For example, when you have two magnets. So, when you want to draw a force, you can do that by using a vector. What is a vector? A vector is when you represent something using an arrow. For example, this arrow right here. And it has four components. It has the magnitude, that is the size of the arrow. You have direction, that is the inclination of the line. Imagining that the line is a simple line and not an arrow. You have the sense of direction, and that is where the arrow is pointing. So in this case, it's pointing up and to the right. And finally, you have the point of application, that is the origin of the arrow. For example, here, right here, that is where the arrow started. In real life, when you draw forces in an object, for example, this box right here, you consider separately the forces that are acting in the y direction, and the forces that are acting in the x direction. When you have two forces acting in the same direction, both horizontal or both in x, and the same sense, for example here, 40 horizontal to the left and 40 horizontal to the left, you add them together. So 40 plus 40 equals 80. And you have two forces that are acting in the same direction in the x-plane, and they have opposite sense of direction. So this one points to the right and this one points to the left. You subtract them from each other. You do 18 minus 15 equals to 3. Usually in x, the ones in the right side are positive and the ones in the left side are considered negative. Now, the sum of all forces acting in x is known as the net force in x. And what is this symbol right here? This one just means sum all of the forces, all forces in x. So let's do that. In this picture, remember, right is positive, left is negative. You have 15 plus 5 minus, because it's on the other sense of direction, minus 3. And that is equal to 17 newtons. So you have 17 newtons is the net force on X. Now, Y. Same, the sum of forces in Y is equal to 10 positive, pointing up, minus 10 negative because it's pointing down. So I have 0. So the sum of forces in Y, or the net force in Y, equals 0. Please remember, an object will remain or stay at rest or moving at the same velocity unless the net force is different than 0. When you want to study the forces acting on an object, it is usually helpful to draw them. You draw them in what you call a free body diagram. What is this? A free body diagram is a picture that is going to allow you to see all of the forces acting in one object. For example, if you have an apple on a desk, you can draw the forces acting on the apple in the free body diagram. And the first thing you do is change whatever the object is to an empty box or square. Then you consider all of the forces acting in Y, and then all of the forces acting in X. For example, here, what do you have in Y? In Y, you're going to have a force pointing down. That is going to be the force of gravity. And then because the apple is on a table, you have a force pointing up. That is the force, the normal force. So those are your forces on Y. Now, forces on X. You are not pushing the object. You are not touching the object. So you don't have any forces in X. Now let's see this other example. You have a car that is moving at a constant speed towards or to the left. Free body diagram. First thing, you draw a square. Next, let's consider the forces acting on Y. What do you have? If this car is moving, it is on the street. So you have the force of gravity pointing down again. And because of the street, you have the normal force pointing up. Here you have also an applied force to the left because the object is trying to move to the left. And opposite to the movement, as always, you have to the right the force of friction. In the last two examples, you had an apple that was not moving and a car that was moving at a constant speed or a constant velocity. So that means the forces acting on X and Y were balanced. So they had a net force of 0. But what happens when a car is moving and it's accelerating? For example, in this case, a car is moving and is accelerating to the right. Let's check the free body diagram. First thing, you guys know, draw a square. Next, consider forces in Y. Let's see over here. As usual, you have your gravity down and you have your normal force up. You guys see that the object is not moving down or moving up. So you know the net force in Y is 0. So the normal force is equal to the gravity force in this case. Here 10 is just a random number I invented. For now, this shows you that normal force and gravity force in this object are equal. Now let's consider forces in X. The car is trying to move to the right, so you have an applied force to the right. And as usual, friction goes the other way. So force of friction. But what happens? The speed is not constant. The car is accelerating to the right. That means the velocity increases as the car moves to the right. That means that the applied force is going to be bigger than the friction force. For example, here 50 newtons and here 5 newtons. The net force is bigger to the right. It's the sum of 5. You have 10, and that's pointing to the right. So the object is accelerating to the right. Let's try another one. You have again a car, free body diagram, square. Let's consider the forces in Y. It says the car is moving and is decelerating to the right. Nothing about up and down. So you have your gravity force down, your normal force up. Object is not going up or down. So the net force is 0. So the normal force equals the gravity force in this object. You have that the object is trying to move to the right in X. So you have an applied force to the right. And as usual, your friction to the opposite side of the movement. Force of friction. But in this case, what happens? The object is deaccelerating to the right. That means the more right it goes, the smaller the speed. In this case, the force of friction is going to be bigger than the applied force. So let's go with the last example. One day, you were in 10A and your friend was giving a test in 8A. 10A figured out, they discovered the answers to the exam of 8A, but they couldn't go out of the classroom. So you decided to use a rope to lower the answers through the window. And these notes are moving at a constant speed. So constant speed. Let's check the forces acting on these notes, shall we? First thing, you have a square, free body diagram. Forces acting in Y. Usually you have your gravity force acting on this object. The object is not on a surface, so no normal force, but you have this rope over here. So this is tension. Remember, every time you see a rope, it's tension. Because it's at a constant speed, you know that the net force in Y equals 0. So the force of tension minus the force of gravity equals 0. So they are the same. Let's say 10 newtons and 10 newtons. Let's consider forces in X. The object is not moving to the right or to the left, so no forces acting on X.